I'm going to be talking about gravitational fields during today's lesson. And a gravitational field is defined as the region of space surrounding a body in which another body experiences a force of gravitational attraction. Now, what might be sort of revolutionary to find out is that all objects with mass have gravitational fields around them, meaning all objects with mass are actually attracting all other objects of mass. Now, luckily, as we're going to calculate a little later on, the force of attraction, for example, between me and the desk I'm sitting at, or, two pencils sitting in my pencil tin, is not significantly large, so we don't really notice anything going on with that. We're much more likely to notice the gravitational attraction of ourselves towards the Earth, for example. But there is still a force that's going on there, and we'll be able to calculate it. Now we're going to be looking at gravitational field lines, and these represent the direction another mass would experience a gravitational force at a point in space. Now we're going to be drawing a lot of fields, gravitational, magnetic, and electric. And it's important to note that these have very specific rules defining how we actually draw them. So when we're drawing fields generally, they're representing vector fields. Now remember, vectors have a direction, and they also have a magnitude. So our vector field is going to be communicating both the direction of the field, but also the strength of the field. Now, some other rules for fields that we need to know. Field lines cannot intersect or touch. Now, the distance between field lines indicates the relative field strength. So if we have close field lines, for example, I've got some here, and we need to put arrows to indicate the direction, this would be a much stronger field than something that was just like this. So we'll see some examples of what these fields look like in a moment. Now, some things to know about gravitational fields specifically. We need to note that gravity can only attract. We don't have such a thing as anti-gravity or anything like that. So that means it cannot repel. That's not true of all fields, but gravity is definitely an example of one that cannot repel. Now, when we have our field lines, due to a mass, they point inwards towards that mass. Because any other mass placed within the field of the original mass is going to be attracted to it. So the field, remember, represents the direction another mass would experience a gravitational force. We're going to have lines pointing into that original mass. So some terminology that you need to know about: uniform versus non-uniform fields. So a uniform field is where the distance between field lines is constant, aka the field lines are parallel. So a nice example of that is when we're nice and close to the surface of the Earth. So it could be talking about here or here or here or on the top of this tree. The field is relatively uniform for when we're standing on the surface of the Earth. Now, the cool thing about a circle is when you zoom in really, really close, it appears to be flat. So here's a nice little GIF here. We're zooming into our circle, and when we zoom in sufficiently closely, we can approximate that to be a straight line, which is what we do when we're talking about fields on Earth. Because we are so small relative to the curvature of the Earth, which is present, we don't notice the curvature of the Earth, therefore it looks locally like the area around us is flat. Again, locally, not globally. And that means that we can look at those field lines and say, well, if they're perpendicular to the surface and the surface locally appears to be flat, using the assumption that it's uniform field when we're on the surface of the Earth isn't too bad. So that means when we're looking significantly further out in space, when we're talking about a location here versus here, we can see the distance between field lines here is significantly smaller than the distance between field lines here. So that's definitely a non-uniform field. So as I said, when we're looking locally on the Earth or in some other different situations, when we have parallel field lines, that's a uniform field. But when the distance between those field lines is changing, it's a non-uniform field. Now, the cool thing about these field lines is they actually extend out infinitely across the universe. But you can imagine if we're going infinitely out in these situations here, the further we go out, the further apart these field lines are, and the weaker the gravitational field is as a result. Now, something we'll look at a little more when we talk about gravitational fields and electric fields is the concept of poles. Now, in gravitational fields, we talk about them being monopoles. We only have one direction that the fields are going to go, and that's towards the mass. When we're talking about north and south poles in magnetic fields versus positive and negatives in electric fields, we can have field lines going into or out of things in those examples. Not true with gravity, we only have one situation. So we'll revisit that a little later. So let's look at an example. We want to use arrows to indicate both the direction and the strength of the force on a mass at different locations. So we're going to just do the strength roughly. We're going to learn the mathematical relationship behind that a little bit later. So let's just say we have a mass here, and we're talking about the field that this mass here has. So if we put a little mass here, we're going to have the force on that mass is going to be towards the center of mass of this one here. Now, these dotted lines here, they're showing if I put another mass over here, that would have the same size arrow, because you'll notice that the distance between field lines here is the same as the distance between field lines here. These are sometimes referred to as equipotential lines, or in fact, because this is a three-dimensional situation, equipotential surfaces, but don't worry about that yet. Okay, let's do it a little bit differently. Let's have something that is over here. Now, the distance between field lines in this situation is significantly larger. So that means we're going to have a smaller force pointing in this direction. Now, we said we're doing it roughly here. We're not doing exactly correct in terms of the size of the force. For now, all I need you to understand is that the size of the force will be smaller on a little mass we put here and larger on a little mass that we put here. Now, those little masses that we put in that field are sometimes referred to as test masses. And I just imagine those to be a little mass. I know that it's going to experience force due to gravity because all things with mass experience the force due to gravity. And I imagine that test mass doesn't have a field itself that's interacting with that field. Okay, let's actually look at how to calculate gravitational field strength. Now, we're going to be using lowercase g, which we've met before. Lowercase g, we've also said, represents the acceleration due to gravity. So I'm just going to put that in our note here. Acceleration due to gravity. We used it extensively in our first topic, and we're going to be looking at situations where we're not just confined to the surface of the Earth anymore, when g is equal to 9.8. Now, as I mentioned before, g represents the gravitational field strength. It also represents the acceleration due to gravity, and that makes sense. The strength of a gravitational field is going to tell us how fast it's going to accelerate due to that field. So let's look at this other equation for g. We'll recognize some of these things before. So g we said was gravitational field strength. Let's just write grav field strength. Now the units actually newtons per kilogram. And if you did a dimensional analysis, you would find that the acceleration due to gravity units, well, it's acceleration, so it's just meters per second squared, that's actually equivalent to newtons per kilogram. And that makes sense. If we're talking about gravitational field strength, it's going to tell us how many newtons of force it's going to apply on each kilogram of mass that's inside of that field. So let's look at these other values that we've got here. Now, we've got uppercase G. It is critically important that you do not confuse lowercase g, uppercase g, and remember in the past when we've talked about Fg being the force due to gravity, that's F subscript g. Really important that we keep those all distinct. This one, this capital G, is known as the gravitational constant. And it has a value of 6.67 times 10 to the negative 11. Now, it has some crazy units. You don't really need to know them, but if you find it useful for dimensional analysis, it's Newton meters squared per kilogram squared. Again, you don't need to know that, but if you like looking at the units of equations, please have a check out of that. Now, capital M here, this represents the mass making the gravitational field. And we're going to measure that in kilograms. So for example, if we were looking here, we'd be interested in this mass here, not the masses of the little test masses that we put inside of that field. Now, R's the last value that we need to look at here. This is the distance from the center of mass to point of interest. And because it's a distance, we're going to be measuring that in meters. So the reason I mention the center of mass here is we're going to be measuring from this center of mass to just say, I don't know, a point over here. That might be our point of interest. We need to do from the center of mass because we're often looking at really, really large objects. And we assume for the purposes of our calculations that the mass is completely concentrated at that center of mass. Now, when we're doing calculations, that works just fine. The problem is that doesn't work if we start burying into our mass, which we'll look at a little bit later. So if we were doing a calculation, we wanted to find the force due to gravity on a satellite that was orbiting the Earth, we'd look at the center of mass of the Earth, and that would work just fine. So some things that we also need to keep in mind. It only depends on the big mass, or the one creating the field. So in the example that I mentioned before with the Earth and the satellite, mass of the satellite doesn't matter. When we're looking at the gravitational field strength of an object due to the mass m, which I said was that capital M, all that matters is that big mass creating the field, because that's going to tell us about the strength of the field, the mass, how massive it is that creates that field. So let's do a calculation here. We're going to actually calculate the gravitational field strength on the surface of the Earth. Now, some things to keep in mind. We'd be given the Earth's mass and the Earth's radius. Now, keep in mind, if we're talking about the surface of the Earth, and we define r to be the distance from the center of mass, when we're on the surface, we need to use r equals 6.37 by 10 to the 3. Now, notice that's kilometers. Let's write that as 6.37 by 10 to the 6 meters. They tried to trick us there, but they couldn't do it. So please, please, please remember, it's got to be from the center of mass. That's where people tend to make mistakes. Now, we've got the Earth's mass and the Earth's radius here, and we're going to do g equals gm on r squared. Just note that those values for the mass and the radius have been rounded a bit, so that might impact our answer. So, capital G was that new constant that we met, 6.67 by 10 to the negative 11. We need to multiply that by the Earth's mass, 5.98 times 10 to the 24. And then we need to divide that by the radius, 6.37 times 10 to the 6. Pause. This is where people commonly make errors. You must remember that we're squaring this on the bottom here. That is probably the number one mistake. Actually, maybe number two. There's another kind of error that people make that I'll talk about a little bit later. So, pop that into your calculators. If you haven't done so, can I really encourage you to make sure you're using the fraction template in your calculator? It means that you're not going to accidentally do BIDMAS incorrectly or have to put in 100 brackets to make sure what you get is the correct calculation. So if we do this to 3 sig figs, that would be 9.83. And the units in this example, in this context, we'd call that newtons per kilo. And the units for this would be newtons per kilogram. Again, meters per second squared would be equivalent, but in this context, it'd be nice to say newtons per kilogram. So, note, that's really close to our value of 9.8. A little bit off, because as I mentioned, the Earth's mass and the Earth's radius have been rounded a bit here. That's a pretty good calculation there. Now, talking about some proportionalities of what we have going on here. When we have G equals capital G m on r squared, that tells us a few proportionalities. It tells us that the gravitational field strength is proportional to the mass that's creating that length, that field. So that means if we double m, we therefore double G, provided everything else remains constant. That capital G has to remain constant because it's literally called the gravitational constant, and just say we were staying at the same radius away from a planet and it spontaneously doubled in mass, then it would spontaneously double its gravitational field strength. Now G is actually inversely proportional to r squared. This one's interesting here. So we would say that in words, G inversely proportional to r squared, or proportional to 1 on r squared. So that's interesting. That means if we double r, think about it like this. If we doubled r is on the bottom of our fraction. So you might think, well, if we double r, then G is going to be halved. But no, we've got to consider r squared. If we double r, we're going to have, imagine it to be 1 over 2 to the power of 2. If we double r, that therefore means, G divides by 4. Some people like to consider it like this. If r times by 2, then what does that do to G? Well, they like to imagine the multiplication becomes a divide. That's the inverse that we were talking about before. And we're going to square this. Square. So this is known as an inverse square relationship. Inverse coming from changing multiplication to division, and square coming from, well, squaring it. So some people like to imagine if I doubled r, then that means I'm going to divide the value of G by 4. What I'm actually doing is multiplying by a quarter, but that means the same thing. So if I tripled r, I imagine what would happen to G? Well, times by 3 means that we're going to divide the value of G by 9. What would happen if I halved r? Hopefully you can see that means we're going to multiply the value of G by 4. Okay, so let's look at an example here. A new planet's been discovered that has the same mass as Earth, but a radius half that of Earth. What would the gravitational field strength, that's G, on the surface of this new planet? I missed a B there. What would be the gravitational field strength on the surface of this new planet? So, as we said before, G and M are constant. Therefore, that means if we have G equals Gm on r squared and the numerator remains constant, that means that G is inversely proportional to r squared, or G is proportional to 1 on r squared. So therefore, if what are we doing? Half the radius of Earth. Half r. That means r is dividing by 2. That means the value of G is going to do the inverse of that squared. So G is going to be multiplied by 2 squared, which means G is going to be times 4. So that means that G on this planet is going to be 4 times G of Earth. So that's going to be approximately 39 newtons per kilogram. So I'm pretty glad that our Earth isn't that radius length, because we would be very squished. Okay, so at one point on the Earth's surface, we're looking at an exam question now. It's a distance r from the center of the Earth. Let's draw a quick little sketch. That is an excellent circle, so that's r. And it's told us at this particular point that the value is 9.76 newtons per kilogram. Which one of the following is the closest to the Earth's gravitational field at a distance of 2r above the surface? Here's that common error that I said I was going to mention before. If we're 2r above the surface, so that would be maybe 1 radius, 2 radius. If this distance is 2r, that's not the distance that we're actually interested in calculating here. We're interested in calculating the distance from that center of mass. So the distance we care about, whoops, accidentally erased. The distance we care about is this distance here, which is in fact 3r. So when we're looking at the gravitational field here, if we've multiplied the radius by 3, that means the value of g is actually going to be divided by 9, or 1/9 of what we had before. So if we do the value that they quoted for g divided by 9, we get a value that is closest to A there. Okay, looking at another example here. We want to use the data above and we're going to do some calculations. So we've got a space station, we've got the Earth and information about that, and the gravitational constant has been kindly provided to us. So we want to calculate the gravitational field strength, this should say on a person, within the International Space Station. So we're going to use G equals G m on r squared. So that's 6.67 times 10 to the negative 11. Now we're interested in the mass of the Earth here. So we're going to do 5.98 times 10 to the 24. Let's divide that by the radius. Now, the situation here, we've got the radius of the Earth and we've got the space station's distance above the Earth's surface. If we're dealing with the Earth here, this is the radius, and let's call that the space station. The distance that we care about is the total distance from the space station to the center of the Earth. So that means we need to do both of these values and we need to add them together. So let's do a bracket because we're going to have to square them. 6.37 times 10 to the 6 plus 4.00 times 10 to the 5 squared. So there's two things that we can make mistakes with here that we need to be especially vigilant for. Looking at the distance from the center of the Earth, adding on the distance above the surface of the Earth, and in fact there's another one, making sure we square it. So popping that one into our calculator, we're going to get, double check this one because I did this earlier, 8.70 newtons per kilogram. Okay, it says use this result to find the magnitude of the force due to gravity on the person. We haven't been given this data, but let's just say M person equals, 200 kilograms. So if we do that, remember Fg was equal to mg. And if the mass of the person is 200, we pop that in. Now be careful. G does not equal 9.8 at this distance. G equaled 8.70 newtons per kilogram. So that means we're going to have times 8.70. So 200 times that 8.70 equals, we'll just do it to 4 sig figs, whatever, 1740 newtons. Nice. Now another good thing to note here, Fg did not equal 0. The force due to gravity is not 0, meaning this person has a weight. They're not weightless. Remember, they feel weightless because Fn equals 0, and that leads to a feeling of weightlessness. It's just a feeling though, because they indeed still have a weight. Weightlessness. Oh, that got a bit messy in the end. So state the two bodies involved in the force interaction above. We had the person and we had the Earth. And then it says, therefore, state the force on the Earth due to the person on the space station. So that's going to be F on Earth by person. This is a Newton's third law situation. We have two bodies exerting forces upon one another. So that means it's going to be that 1740 newtons, and let's just put towards the person. Okay. So let's look at this one here. We've got a physics student has found themselves stranded on an unfamiliar planet. They're fine. They have food and water and oxygen. That's probably their main priority. It says they're armed only with a spring balance that measures the force due to gravity upon them. They know their mass is 70 kilos, and they know the force upon them is about 1750 newtons. We want to compare the acceleration on this planet to that of Earth by expressing the percentage G planet on G Earth. Okay, so in this example here, you'll notice we had two ways that we could really talk about G. We could use Gm on r squared in this example here, but with the information you'll see we have in the next question, we don't have any information about the mass of the planet or the radius of the planet. So what we can actually do is use this rearranged to find out information there. So because we don't have G planet, mass of the planet or radius of the planet, we're going to use G equals F on M. So if we're looking at G, we'll call it this planet, that's going to be the force on this planet divided by the mass of the person. And if we look at G Earth, that's going to be the force of this person due to the Earth, first on this person due to the Earth, I should say, divided by, again, the mass of the same person. So that means, therefore, if we do this, G planet on G Earth, that's going to be F planet on M divided by F Earth on M. I've just used what we came up with here, meaning we're going to have F planet on M times M on F Earth. Now this is lovely because we can actually cancel off these masses here. So we can have F planet on F Earth. Okay, the force of this person on the planet is 1750 newtons, and the force that this person would experience on the surface of Earth, well, that's going to be our standard 9.8 times 70. So that's going to be about 686. If we do this calculation then, we're going to have 1750 divided by that answer that we had before. Remember S to D, that gets us from our fractions to our decimals, so that's about 2.55. Now because this is a ratio, F planet on F Earth, then we have the units of newtons divided by newtons cancelling off. Now looking at this table here, you'll notice that we've got the masses, we've got the radii of each of these. They're not all planets. You notice that we have the sun and we have the moon, but everything else is a planet in our solar system. And we've been given the acceleration due to gravity here. I should possibly have used 9.81 in this calculation that we had before, using the data we had in the table, but oh well. You'll notice when you do that, you get the same amount of 2.55 when you do it to 3 sig figs anyway. Now, we've got G on G Earth, meaning we've got G of the planets or the sun or the moon. Looking down these values in our table, we can see our 2.55 is closest to Jupiter. So our best guess of what planet we're on is Jupiter. Now we know that this student would be in a whole lot of trouble not worrying about what planet that they're on, rather getting squished if they were on Jupiter, but oh well. Okay, so the same symbol G is used to represent the gravitational field strength, which we measured in newtons per kilogram, and the free fall acceleration, which we measured in meters per second squared. These are actually equivalent units. Now, we had these two equations that we could use for it. If we know the force on small mass and mass of, this looks funny, small mass, like we had in that last question, we would use G equals the force due to gravity divided by m. If instead we knew the mass of large object and distance from center of object, we would use our second value. We would use our second equation here. Little g equals capital GM on r squared. So that's the main takeaway from this lesson, the two different ways that we can calculate either known as the acceleration due to gravity, aka free fall acceleration, aka the gravitational field strength. There's these two different equations that we can use.